So one of the things I was trying to share with you, I almost stopped here on Thursday, and all I said was, whenever you detect ions, the carbocations that are most stable are going to be the more prevalent ones. So here we have methyl. You can see that methyl is not very stable, so we're not going to see much of this. Then primary, then secondary, tertiary, and then these resonance stabilized carbocations such as the allylic one and benzylic ones are significantly more stable. Okay, so we see this trend, and so statistically, if I have any one of these pathways, we'll see more and more of these amounts. Okay, so a little bit later on, I'm going to basically come back and I'm going to show a system where you see quite a bit of allylic carbocations. Okay, again, recognize that allylic carbocation here. If I push this electron over here, basically I get a carbon right here with a positive. So the way I look at resonance is I have two resonance structures in which both of these terminal carbon atoms have a half a charge. And so one of the reasons we say resonance is stabilizing is that I'm spreading charge onto more than one atom. Okay. And so this is basically what I'm showing you. Again, a lot of books do it this way. Obviously, one structure of that is I push the electron to form the methyl radical. But again, probability is I could have pushed that electron in the opposite direction. Okay, so again, you have a choice of where to push that radical cation. You want to push it onto the right of that bond or onto the left of that bond. Okay, again, that direction just depends on the stability of that carbocation. Okay, obviously, we're going to push the electron in the direction that's going to lead to the more stable carbocation. So here is a spectrum of hexane, and you can see in the spectrum of hexane that, here we have a molecular ion peak. Okay, so here is my M plus peak. So it's pretty prevalent, but notice that the base peak here is 57. And again, we define the base peak as the largest peak that shows up in the spectrum, and we define the largest peak as intensity of 100, and everything is relative to that. Okay. So what I pointed out to you guys is that, again, you can look at it this way. I'm not going to go through all this, but again, if I see this, obviously I'm pulling the electron on this carbon-carbon bond here, okay? And then if I have a single electron, notice I'm pushing that electron towards the methyl group because methyl radicals are going to be a lot better than making the methyl carbocation. That leads to a primary carbocation here, which is a base peak, which is a peak that shows up at 71. So notice it's pretty small here. It's only 71, again, because it's primary. OE here with 57, my base peak here. So notice I'm breaking this bond here because I'm forming a 4-carbon here, and then I'm forming a 2-carbon fragment. So if hexane 6 carbons, I'm breaking that bond right here. I'm breaking it in the direction in which I form an ethyl radical. Okay, so if I push the electron here, I get this. Again, I form a primary carbocation, but recognize ethyl radicals are a little bit, primary radicals are a little bit more stable than methyl radical. So again, we're seeing that as 57. What's interesting though, is notice that if I push the electron, if I take out if this bond has 2 electrons here, and if I do electron impact ionization, I remove electrons, so I form a bond with just 1 electron. If I push that electron here, I get the top one, but now if I push that electron in this direction, I get a butyl radical plus the ethyl carbocation. And so the ethyl carbocation, it shows up at 29, here it is, okay? Again, my point here is that it's not very discriminatory. It basically, particularly of alkanes, it can basically take off any of these atoms, between any electrons between these carbons, as well as the hydrogens. So I don't even show that. Also recognize I could either go in either direction, for shown here and this one here. But the other important part that I just want to remind you guys is recognized in the mass spec. The only thing we see are atoms or fragments that have a positive charge. And again, it comes in 2 flavors. It's either a radical cation or carbocations here. Notice that we don't see these species here. So although I have this fragmentation here, I get a peak for a methyl radical here, I get a fragmentation of methyl radical. Since methyl radical is neutral, it doesn't show up in the mass spec. So notice I don't have a peak right here in around 15. Okay, so again, anything that's not neutral will not show up in the MS spectrum. Okay, only positive, so either radical cations or cations. I finished my presentation last time on this one, so let's just review this. Hopefully it makes a little bit more sense to you now. So here is neopentane. Okay, so neopentane is a carbon that has 4 methyl groups around it. Consequently, we say that this central carbon is quaternary. Okay, so it's a quaternary carbon. Basically, quaternary carbons mean carbons that don't have hydrogens. So here I have neopentane with this carbon, and notice that if I do electron impact ionization, I'm going to remove an electron from one of these bonds. Since it's very symmetrical, let's remove an electron from that bond here. Okay. Again, what direction will this go? If I take the radical and place it onto carbon, I would get a tertiary radical, but then I would get a primary carbocation, a methyl carbocation, which is not very stable. Instead, we're going to take that electron and move it towards the methyl. That gives me methyl radical here, plus a tertiary carbocation. Okay. So again, the biggest peak in this spectrum here is the peak that is for the tertiary carbocation. Again, to think about this, this is 15 plus 15, that's 30, plus another 15, that's 45. 45 plus 12 is 57. So this is basically the loss of 15. The M plus peak minus 15 is 57. So this base ion peak right here, this base peak for this spectrum is for the tertiary carbocation. The important point here that I also pointed out to you guys on Thursday is here is an example of where one sometimes does not see the molecular ion peak. So the molecular ion peak for neopentane should show up at 72. Notice that there's nothing there. And the reason for this is on the time scale, before I observe this, this molecule wants to fragment faster than I can capture this because the tertiary carbocation is just significantly more stable. Okay, so this is an example of not being able to see the molecular ion peak. Again, one of the things I'll point out a little bit later on today is that there is another technique that one can actually use to observe the molecular ion peak, and that is not through electron impact ionization, but rather using chemical ionization, which I'll talk about later on. All right, any questions up to this point? This is not too exciting. There's more exciting stuff to come. Okay, so let me move a little bit forward.